Thank you all for joining us again tonight. It's great to be back with you. A lot of familiar faces, a few new ones. Hope you enjoy our presentation tonight on the stars. I'm always thinking, what can we do next? And here we are. Their birth, life, and death. So boy, do I got a lot to tell you, as a few of my students can vouch for. We've been studying this lately. How many of you experienced a scene like this before? Have you ever been out somewhere really dark and seen the stars? Not just the few we see around here. Oh, that's nice to hear. If you haven't, make it a point someday. Take a camping trip to some place and go see the stars like they really deserve to be seen. As I always say, there's so much to tell you in 1 hour. I will do my best to keep it to an hour, and then afterwards we'll take some questions. But here are the four main parts to this presentation that I'd like to discuss with you. First, we'll talk about where do stars come from? How do they form? Okay. Then their properties. How do we know what we know about them? I used to call them sometimes those little dots of light in the sky. How do you possibly know what those are all about? Their distance, their size, their temperature. All these kind of things help us know them. Okay. Then we'll talk about the life cycles of stars. They form, they essentially are born. They live through certain stages, go through various phases, and then they die, whether it's quickly or taking a long time. So again, fascinating story there, and then we'll again focus in and finish with how those stars die. So you ready to get to it? Let's get started, shall we? Where do stars come from? Well, out in space, there's a lot of raw material, the building blocks, perhaps we could call it. Gas, dust, other stuff floating around. Now, it's not very dense, except in a few places, as you can kind of see here. We call these nebulae. That's a word that goes way back. Early astronomers looked at these with their early telescopes. So it looks kind of like a little cloud. That name kind of stuck, so we still call them that. Here's where the dust, the gas is concentrated together, and conditions are right for stars to begin to form. So how does that work? Well, you can probably guess, gravity is the driving force here. It is going to essentially do the work of forming the stars from these raw materials, but obviously that's a big question, right? How does gravity turn raw materials into stars? So I'm going to take a few minutes to discuss that. Then we'll get to the various properties of the stars, okay? First of all, these clouds come in various sizes, many different masses, okay? Different properties. But you can see here the things that are important are, number one, a high enough density of material. Why? Well, that means gravity will be stronger. It will be able to form stars. And second, temperature is actually important. If our cloud is too warm, that implies that it's going to have a little bit stronger outward pressure that's going to resist gravity, and it's going to inhibit star formation. So what we really want is a cloud that is relatively high density, relatively low temperature. And obviously, since there are many, many billions of stars, this works. Nature's pretty good at making stars. There's so many of them. Okay, so you can see some typical numbers here behind me. Temperatures as low as 30 degrees Kelvin. That's like minus 400 and something to you and me. Okay, density 300 particles per cubic centimeter. Is that a lot? No, that's not a lot. That's better than our best vacuum. So this stuff is extremely low density, and yet again, obviously there's no air in space. Gravity can do its work slowly, steadily, relentlessly, forcing this material, contracting this material into stars. Given these two numbers, you can see that we need our cloud to have a minimum of about 200 times the mass of the sun. We know that because of this equation at top right here. You can see T for temperature, you can see, can't read that, N for density. And if those conditions are met, then gravity can do its work. So that equation essentially is based on the strength of gravity being able to take that mass, that density, and that temperature, and get this process to work, okay? And again, the good news is we obviously see so many stars, and we see these birthplaces of the stars are quite common. So let's walk through just for a minute here a little bit of the stages. You see kind of in the extreme upper left there a huge cloud, and gravity, as I said, is going to slowly contract this thing over, as you can see, a long period of time, many tens of thousands, hundreds of thousands of years even, okay? And three things are going to occur as gravity is starting to contract this cloud. Number one, it's going to heat up. Why is it going to heat up? Well, you need to think of it as these particles slowly being accelerated by the gravity. Their velocity increases. That's a simple, almost crude way to describe temperature of a gas, is the velocity of the particles, okay? Some of you might be familiar with the concept of potential energy. If we have a huge cloud with particles very far apart and they begin to fall inwardly, gravity is the acting force here, and the energy that they have as a potential is now changed into greater velocity or greater thermal energy. So the cloud begins to warm up as it's starting to contract. Second thing you can see there, it's going to start to spin. Why would it do this? Well, no cloud made of particles like that is going to be absolutely motionless in space. It's going to have a certain kind of preferred overall motion. Yeah, it has different parts moving in random directions, but overall, sooner or later, there's going to be a net effect to this. And the idea is that as this thing is contracting, it will slowly begin to spin due to another concept maybe you've heard, angular momentum. So this is just a little touch of physics here, but it helps us understand why does the cloud do this. And you can see there in the third image to the right there that as this thing is starting to spin, it's going to flatten. It's going to flatten into a disk. Why would it do this? Think of it this way. Material that is, let's just call it above and below the spin axis, is free to fall inwardly. But as this thing is spinning, there's a centrifugal force that's going to oppose that perpendicular to the spin axis. And so this flattened disk is going to form around our young protostar at this point in time. Later on, that disk may form planets. So you can already see here at an early stage how these various physical concepts come into play and will eventually result in a star. As we'll see in a few minutes, stars may take varying amounts of time to form. Some that have more mass, gravity is going to be stronger. They're going to contract and form quicker. Others with less mass, gravity is not quite so strong. They're going to take longer to form. You'll hear me come back to that once or twice here in our discussion. So this is what we call the nebular theory of star formation. And it essentially, as I just described, uses the various physical concepts we know about to explain how you go from a big diffuse cloud to stars. There's a few more steps, but I think you get the general idea here, how gravity is the driving force as it works through these different stages. Now, I'm not going to read you every part of these little diagrams, don't worry. But at this point, we begin to call the object a protostar, okay? This cloud is not going to take all of its material to form one gigantic star. It's essentially going to break into smaller fragments, so to speak. And these fragments will continue their contraction because now they're a little denser than the surrounding material, okay? And as they're, again, getting smaller, contracting, as we just said, they're going to heat up in temperature. They often begin to expel what we call a stellar wind to blow away some of the infalling material. That may or may not be a good thing for this young star. It still needs to gather more mass. Okay, so that's kind of another factor in this thing. And for the moment, I'll explain this in a moment, but we're going to call it a pre-main sequence star. You'll see why in just a few minutes. As it heats up, gravity is having to fight that energy that's flowing outward But again, as I said, we see stars forming all around us all the time. So this obviously works. Gravity is able to overcome that pressure. The denser the star gets, the hotter it gets, especially in the center. So when is it a star? You can see the magic number there. About 10 million degrees in the center of this object, a dramatic change occurs. A dramatic change occurs. We're going to talk all about nuclear fusion. Nuclear fusion. In this case, stars are made of hydrogen, so it's going to be hydrogen fusion. And this is a dramatic increase now in the energy, and that is going to now balance gravity compressing this cloud. So picture it being driven smaller, 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 and then the burst of energy says, nope, that's just about enough of that, and we're going to find a balance. It may take it a short time to kind of reach an equilibrium, but when the center of the star reaches that temperature and starts to generate this tremendous energy, now we have a new star. So it's interesting to walk through some of those stages, understand how it happens, because that will help us understand the star in general. Okay? So we go from that protostar to the pre-main sequence star, and now we have an actual star. It's going to find that balance. It's going to be able to emit plenty of energy. Okay, so at this point now, we can then say, well, that's interesting how that forms. What can we know about these stars' properties? And here we're going to spend some more time figuring out about these little dots of light in the sky. Now, it turns out there's a number of things we need to know to understand them. I'm going to start with distance. Why distance? Because until we know the distance, it's very difficult to figure out the other properties of the star. Okay, so how do we figure out distance? Have a look there at that little animation. You can see a star that appears to be moving back and forth left to right. Let me kind of restart that just quickly. Watch closely. In the bottom, you see the Earth going around the sun, and we're looking out at that little star. And it appears as we orbit the sun that it's going to move back and forth. But notice how if it's farther away, the shift in its motion is less. It's a little bit like if you were ever to hold your finger out in front of your eyes real close and open and close each eye, you can see your finger shift back and forth. But the farther away you hold it and do that, it doesn't shift very much, does it? And something across the room doesn't shift at all as you do that. You're looking at it from a slightly different direction with each eye and essentially seeing it at a little different angle. That angle is what we're after. Look to the diagram there on the right. Notice how, again, we're showing here greatly exaggerated, Earth orbiting the sun. We know the distance of Earth to the sun. Most of you are familiar with an astronomical unit. And we've greatly, again, stretched our picture down for you. But the point is, notice that little angle there. See that? That the star appears to shift by? That's because it's relatively near us. The amount of the shift is dependent on the distance. And so when we measure that shift, when astronomers measure that shift of the star over the period of a year, we have a simple equation that gives us the distance. Pretty nice, isn't it? That we can use a simple concept to find their stars. So we began doing this, way back in the 19th century. Early astronomers were starting to determine these, and over the time, of course, very painstaking, very tedious work to measure these little shifts, but it enabled us to learn the distances of stars. Some, of course, were so far away we didn't see a shift. But then we knew that they were far away, didn't we? They had to be greater than some particular distance. So parallax is the term we use for this shift. It's the annual motion of a star seen because Earth's orbiting the sun. And we're viewing it from a slightly different perspective in January compared to June. Okay, so all during the late 19th century, early 20th century, astronomers were very busy, working very hard to measure these. These days, we have technology to help us. We have satellites that can measure it far more accurately than we could ever do it manually. The European Space Agency launched a satellite that was able to do that to exquisite precision, and we now know the distances to stars to much better accuracy than we ever did before. Okay, so we have the distances to stars. What will that do for us? Well, notice my final comment here. If we know the distance from the parallax, we can now find the luminosity from the brightness. So let's right here then make a clear distinction between those two terms. We have to use them carefully. Brightness is how bright something looks to you and me. But even though these bright lights are shining on me, if you were to take them 1,000 feet away from me, they wouldn't look so bright, would they? But their luminosity is the amount of light or the intensity of light that they give off. So we may look up at night and see stars of various brightnesses, but those brightnesses depend on distance. Are they far away or are they nearby us? If we can determine that, which we can, then we can figure out the luminosity, which is the next property of stars that we want to talk about. So luminosity, again, is the total light emitted. Brightness is what you and I receive based on the distance. Okay? So look in the upper left, and you can see a diagram indicating how light spreads out over greater distances. What's real interesting here is if we measure the intensity of light at the first distance, there 1 AU, and then we measure it at 2 AU, twice the distance, you might just naturally think it should be half as bright, but it's not. Look closely, and instead of the light being measured over one little square, at twice the distance, that light has spread out over 4 times the area, or 4 little squares. Do you see that? At 3 times the distance of original, it's spread over 9 squares. Can you see the relationship here? The square of the change in distance is how much area it's spread over. This is why we call it the inverse square law of light. This is how light's intensity diminishes over distance. So you can see the initial equation there, brightness, luminosity, distance squared. Now we don't normally calculate brightness, we normally measure brightness. So we normally turn the equation around, as you can see here, because what we are really after is the luminosity. So in other words, if we measure the distance with parallax and we measure the brightness, we have the luminosity. Nice relationship for us to be able to use to determine how much light is the star actually giving off. If we really wanted to, we could turn the equation around one more time. If we know the luminosity somehow and measure the brightness, we could actually use it to find distance. We do that occasionally, but the primary version of the equation is that middle one there. We measure the distance and we measure the brightness. Okay, so what did we find? Look at this diagram here. Can you see the sun? I can't even see it. How big are those stars? Wow, they are really big. And we'll get to their size in just a minute, but the point is there's a tremendous range of luminosity among stars, and size is a big part of that. Let's start with the lower number. The least luminous stars are 1/10,000th the luminosity of our sun. That's not very much, is it? But my goodness, can you see the most luminous stars? 1,000,000 times the luminosity of our sun. I've just never been able to get that or grasp that a star could give off 1,000,000 times as much energy as our sun. Our sun is a pretty powerful star, and yet there are those much more luminous. Okay, so what a tremendous range. 10 magnitudes of range there. In other words, the very most luminous stars are 10 billion times more luminous than the least luminous. What a tremendous range among the stars. How about their temperature? In previous lectures, and maybe many of you are familiar with this, we can take the light from a star, break it into a spectrum. We're looking essentially at the intensity of light versus its wavelength. And here you see several of them, the different colored curves there. First, we have at the top a blue curve for a star that's 15,000 degrees at its surface. The yellow curve is our sun, about 5,800, and the red curve about 3,000. Okay, so what do we see from these curves? If we were to take the light from these stars, break them into a spectrum, and examine them, two things jump out at us. Number one, hotter objects, hotter stars, emit a greater intensity of light. Notice how the blue curve is simply higher than the others. There's just a stronger intensity. It's giving off more light, okay? Number two, the hotter the object, as you see there, emits light of a higher energy. What do we mean by that? Well, along the bottom here we have our wavelength. The shorter our wavelength, the higher the energy. So can you see that again, the blue curve there, notice that dashed line is showing you the maximum intensity of that curve. It's farther to the left than the dotted lines for the sun and the dotted line for the red curve. So in other words, again, a hotter star is giving off a lot greater light intensity, and the light it is giving off has higher energy. There's kind of two different things there. How do we know all that? We know that, as you can see, from Wien's law. My students studied this just recently. Nature's given us a nice simple equation to determine the temperature of a star. What do? We take that curve, we find that maximum, or we call it the peak wavelength, and we plug it in the equation over there. Temperature is 2.9 times 10 to the 6th divided by that number. It's really not that difficult. In fact, if you look, let's just take, for example, our red curve. You notice the dashed line comes down. It's right about at a wavelength of about 10 to the 3rd, or 1,000. So if you plug that number in, you're going to get a temperature of about 2,900. Here we've just rounded it up to 3,000. So the light from the star has this information encoded in it. If we know how to analyze that, take the spectrum of the star by breaking it into the wavelengths, finding that peak, plug it in our equation, we can tell you the temperature of the star. Pretty nice that nature allows us to figure those things out. What's the range? You can see here, the hottest stars can be upwards of 50,000 degrees. Our sun about 5,800. The coolest stars right around 3,000 or so. So there's a pretty good range there, but not nearly as much as luminosity is there. Okay? So we now know the temperature of stars. We know their luminosity, all from examining their light. Well, how big are these stars? I started touching on that just a little bit. Here we also use a very clever way to determine this fairly simply. The radius or size of a star depends on, number one, its luminosity. In other words, how much total energy does it give off? But it also depends on how much energy is given off by one small, you could say, square meter of the surface. One small area of its surface gives off this much. If we know that and we know how much total, all we really have to do is divide the two numbers, and we will get the number of those small square areas. We could then add those up, and we have the surface area of a sphere. Does that make sense? I think it does. So again, it's fairly straightforward observationally to, again, as we just said, determine the luminosity and determine the temperature, as we just saw. Those two numbers you see in the equation here, don't you? R is radius, L is luminosity, T is temperature. There's a couple of other constant numbers there, those funny-looking Greek symbols, okay? But the size or radius of the star depends on these two things that we just explained. So once again, now we can get a very good understanding of the size of stars. What's their radius? And once again, you can see quite a range here, okay? These huge, huge supergiant stars, we work our way down to our sun, and there's stars far smaller than our sun as well. So what a tremendous range of size the stars have. So I hope you can see how astronomers can use many physical concepts to determine the properties of stars. When we can look at them, analyze these properties, we understand them better, don't we? But perhaps the most important one of all is one that all these other things are based upon. So let me now talk about the mass of stars. Mass, of course, is the amount of material. How are we going to measure the mass of a star? Well, we're going to use gravity. Gravity is going to work like a tool for us, essentially. And we're going to use a very specific case here. You can see two stars orbiting around each other. They both orbit around what we call the center of gravity. You notice the brighter one, probably going to be more massive, don't you think? It doesn't move as much as the other one. This is what we actually see in nature, but we could, if we choose, we could just use that more massive one as kind of a center point and measure the orbit of the other one around it if we wanted to do that. That works. And we're going to use a method, as you can see here. My students are going to smile. Newton's version of Kepler's third law. Maybe you recognize those two names, two famous astronomers. They both contributed to this. Isaac Newton put this together in the late 1600s. Look at this equation. Now, it's not as bad as it looks if you're not a math person. The mass of both stars added together, the sum of the two masses, equals 4 pi squared. We probably all know what pi is, right? So what's a to the third? Well, a is the average separation of the stars. We're going to have to figure out how far apart are they on average. They may get a little farther, a little closer, but what's the average? And that's divided by g, which is the gravitational constant. That's just a number we can give you. And p squared. What's p? That's the period of the orbit. So these bottom two factors we must measure. We must determine these two factors, plug them in that equation. We'll get the masses of these two stars. And as I said, that's quite important. So how are we going to do that? How do you measure orbital period and separation? Well, astronomers have developed some very clever techniques. First, let's talk about the orbital period. How can we do that? I'm going to show you 3 different methods for that. The first one was developed quite some time ago, and it's called measuring the period of a visual binary. Notice my diagram at the upper right there. You see the two stars orbiting around their central point. Back in the 19th century and certainly into the early 20th century, astronomers would very painstakingly, very tediously go to the telescope week after week, month after month, and they'd look at these two stars, and they would carefully measure their position around each other as they slowly changed their position. This often took years, sometimes even decades, for them to do this. So my goodness, what a labor that was. But over time, they could tell you pretty much how long it would take for these two stars to orbit around. It's a very simple way to do it, but it required great dedication. The second method was developed a little bit later among stars, again, orbiting each other, but this time it was a very special case where the stars would orbit in such a way, if you're all sitting on Earth, where their orbit would mean that one would pass in front of the other, eclipse it essentially, and then the other would eclipse the other. So if we were attentive enough, aware enough, we could watch this happening and graph the total brightness. And you notice, of course, there's some dips. Where one star passes in front of the other, it blocks a little bit of the star, doesn't it? Blocks some of its light, so the total light goes down. And then it swings around the back, and some of its light gets blocked. Well, you know where I'm going. The time between the dips on our graph is the time of the orbit. Here you actually just see half of an orbit, don't you? But the point is, as they orbit around each other, we could measure when does the light diminish. Let me just kind of restart that for you there. That would give us the orbital period. So that was a little bit easier, actually. And we could do that for stars of varying orbital size. How about our third method here, spectroscopic binary? What does that mean? Well, a few minutes ago, we talked about the spectra of light that we can get from a star. And in some of my other lectures, I've explained how when we look at the light from a star and we break it into a spectrum, we often see spectral lines that indicate various elements are present. And we know what those elements are because here on Earth we can compare okay? But what we also see is that as a star is moving towards Earth, normally its spectral lines, I'll just do this simply, may have a certain position, a certain wavelength, but as it moves towards Earth, that position is shifted slightly of the spectral lines. We call that a Doppler shift. Maybe a lot of you are familiar with that as well. When it's moving towards Earth, it's shifted slightly shorter wavelength or bluer light. When the star's moving away from us, those lines shift slightly redder or longer wavelengths. So the point to us would be, well, let's watch and see if these two stars are orbiting, one's coming towards Earth, its spectral lines will shift one way, but the other star moving away from Earth will shift the other way, kind of like that. Look closely in the extreme lower right there. You notice those lines kind of shifting back and forth? Picture yourself on the little green dot there. That's supposed to be Earth. And the point is, again, whoops, you see those spectral lines shifting. They're going to kind of do like this over time. We just have to measure how long that takes for those lines to shift, and that tells us how long it takes the stars to orbit. So we have three methods to figure out the orbital period of this binary star. Okay, so that's the first number that we need. What about that other number, the separation between them? Well, here we're going to just use, again, a very simple relationship. Let me go ahead and go like this. Think about the orbital velocity. We just said you can get that from how much those spectral lines shift, if it's greater or lesser. We also said we could figure out the period of time it would take for the stars to orbit. Think about what that means. Velocity is distance over time. Period is time. You see where I'm going here? So we can use the velocity and the period to find the distance between them. Look down below. I've tried to simplify this. The separation between the stars is based on the velocity and the period. What's the distance? Think about these stars traveling around in their orbits. They're going to cover a certain distance, the circumference of their orbit. And if we know the circumference of a circle, don't we know the radius? Yeah. So how about that? That's pretty clever, isn't it? We can determine the circumference of the orbit, the distance the star travels. That gives us the radius or the separation. All right, so we've got what we need now. We've got the periods of these binary stars. We've got the orbital separation. Now we can determine their mass. Newton's version of Kepler's third law allows us to plug those numbers in. What do we get? What's the range of masses? Let's start with the lowest mass stars. I'll give you the number right away. The lowest mass a real star can have is about 8% the mass of the sun. Why that number? Turns out if it's any less than that, the center or core of the star is not going to get hot enough to make the nuclear fusion. Okay? Gravity's not strong enough to compress the star and make the nuclear fusion begin. It's not a star. What do we find right at that threshold? We find the surface temperature of these objects is about 2,000 degrees. They're much smaller than the sun because they're not very massive, only about 8% of the solar radius. And they only give off about 1/8,000th as much light as the sun. We said that a few minutes ago. And these are so small and they have such relatively weaker gravity that it takes them a long time to form. Gravity's just not strong enough to form this star very quickly. Okay, so we're getting a sense here of what these are. Again, any less than that, what do we have? In the extreme upper right, you see an artist's impression of something we now call a brown dwarf. Have you heard that term? A brown dwarf? What is a brown dwarf? Well, it's a failed star. Didn't have enough mass to join the club. Didn't get hot enough for nuclear fusion. Is it giving off any light, any energy? Yeah, but not much because it's not very hot, relatively speaking. So these just dimly glow with very dim light, especially infrared light. And they're very difficult to see from Earth for that reason, that they don't give off much light. You can see here we can compare them to a star. Over here, instead of using solar units, let's now switch over and we'll use the mass of Jupiter as just a convenient unit. A star must have at least 80 times the mass of Jupiter. That's just a nice number to say, oh, well, that's how much for the fusion to begin. But notice our brown dwarfs, about 13 Jupiter masses up to 80 Jupiter masses. Kind of this space where they just didn't have enough mass for nuclear fusion to ignite. Okay? How about less than 13? Well, now we're in the range of planets. Planets. So interestingly, some years back, 20, 30, 40 years ago, we suspected these and we had not found them, but now we have, and we can study brown dwarfs. One final distinction I want to make for you here and make sure that you get is that planets form around stars. Brown dwarfs form by themselves pretty much. Sure, we occasionally find them around other stars, sure. But for the most part, they can form independently like a star, whereas a planet is going to form. Remember that disk of material around our star? Yeah, that's where planets are going to form from that. So it's kind of two different processes, so to speak, and thus the distinction. So that's kind of the lower end of the stellar mass scale. How about the upper end? Is there an upper end? Turns out we think there is. The number I'll give you here is about 150 times the mass of the sun. Can you imagine that? Recent research suggests there may be some possibility of a bigger number even, but for now we'll stick with this number. Why that number? Well, as you have a star with this much mass, gravity is so powerful, the star must generate tremendous energy to balance gravity. Turns out that these stars are so big physically and so massive that they are pouring out so much energy that the surface regions of these stars are quite a distance from the center, and that tremendous energy is literally blowing those outer layers off. You can see an image here in the lower right of that. This star is shedding mass at a furious rate, and it's just going to basically work its way under that number eventually. It's not going to be able to stay up above that number very long. Okay? Now, high mass stars, you can probably guess, as it says here, they have that powerful gravity. They are going to squeeze that core very small, very hot. They can form much more quickly than the low mass stars. Okay? So now we have, I think, a good grasp of the masses of stars. We covered those other properties. We've got the masses. What do you think? Kind of a little technical, right? Well, about 100 years ago, a little over 100 years ago, two astronomers were working through some of these basics, and they both came up with a method that I think you're going to like maybe a bit better. Okay, it's more of a graphical method. Sound good? Let's have a look at something that came to be known as the Hertzsprung-Russell diagram. Two astronomers, European astronomer, American astronomer, developed this roughly the same time. This diagram plots the properties of stars' luminosity on the vertical axis, temperature on the horizontal. Let me point out a few things, first of all. That horizontal temperature is the surface temperature. And notice that it increases from right to left, not left to right as we normally might graph things. Luminosity on the vertical scale, I don't know if you can read that or not, but that's an exponential scale, okay? If you look closely, you might be able to see it's just in units of 1, 10, 100, 1,000, 10,000. Those are units of solar luminosity. We can measure the sun's output. It's about 10 to the 30th watts. Okay, 10 to 26 watts, excuse me. And yet we're going to just use that as a unit. Is this star twice as luminous as the sun, 10 times, 100 times? So we've basically taken an enormous scale and compressed it down by making this exponential. Okay, when we do that, we not only are plotting those two properties, but it turns out this diagram is extremely powerful in many ways. I continue to be amazed. Often I'll go to a professional conference for astronomers, and the way it's used is just remarkable to see how some astronomers can use this in different ways. I'll explain a few of them for you here. Clearly, we, again, see and plot the luminosity and surface temperature. But you also notice that our artist has put some colors in there to kind of give you a feel what this thing would kind of look like. Again, some of you might be familiar with the spectral type here we represent with these letters. I won't go into great detail tonight. O stars are the hottest. M stars are the coolest. Okay? Our sun is a G-class star right in the middle there. Okay? And this diagram also allows us to get at a glance a rough estimate of the size of the star. We'll get back to that as well. Okay? Now, interestingly, when we go out and we plot the various stars' properties here, we find that most of them, sometimes up to 90% of them, will fall on this diagonal line from lower right to upper left. And if you look closely, you might see it's called the main sequence of stars. Okay? Also, to the upper right, we have stars that are called giants and supergiants. You can probably guess why. They're quite large. And then down to the lower left, you notice we have the white dwarfs. Probably can guess those are quite small. So in other words, size increases to the upper right, decreases to the lower left. So already we're gaining some more information from the properties that we plotted just by a quick glance. Let's talk about that main sequence a little bit, then we'll come back and we'll talk about supergiants and giants, okay? So what is the main sequence all about? Why do almost 90% of stars lie on there? Main sequence stars are where the stars are fusing hydrogen to helium in their core. This is what our sun is doing. Our sun is plotted smack dab right in the middle of it. Can you see it there? Okay. So for a star to be on the main sequence, first of all, it must be fusing hydrogen to helium in its core. Okay. And then we plot it on here, and you can see this range. Look down to the lower right. You notice they're colored reddish because their surface is cooler. Why is it cooler? These are lower mass stars. The opposite extreme to the upper left, the stars are colored blue. Why blue? Because they're high mass, and their luminosity is tremendously higher. Do you see that? So here on the main sequence, at a glance, we get a very good understanding of stars, what we just walked through. The low mass stars have weaker gravity, lower core temperature, lower fusion rate, lower luminosity. And I also added that they have a longer lifetime. In contrast, our high mass stars to the upper left, stronger gravity means they're going to have a higher core temperature, higher fusion rate, and they're going to pour out a lot more energy, higher luminosity. Because of that, they're going to live a shorter amount of time. So again, at a glance, as you get more familiar with these diagrams, astronomers can quickly read off essentially what the star's properties are without so many calculations. Okay? Main sequence stars. This really makes clear to us the importance of mass. The importance of mass really is the most important stellar property. If you tell an astronomer the mass of a star, we can pretty much tell you all the other properties. Oh, it's high mass? Well, it's going to be hot. It's going to be luminous, it's going to be relatively large, and it's not going to live real long. It's going to burn up its fuel real fast. And likewise, the opposite for the lower mass stars. So here you see a few examples of the sizes of some main sequence stars of different masses. And no surprise, our large blue hot B-class star is exactly that, large and hot. Then we have a star that's not quite so large, not quite so hot. Then we have our sun. I don't know if you can even see that little red speck at the bottom. Can you see that? Proxima Centauri. It's an M-class star. That would be way over on the extreme lower right of the diagram. Very low luminosity, very small size. So it's very convenient, very useful for astronomers to just pretty much always use the HR diagram in discussing stellar properties. Okay? The Hertzsprung-Russell diagram also allows us to learn about other stars, giants, supergiants, white dwarfs. What's the deal with those? Well, let's think about that. Those giants and supergiants we saw in the upper right of the diagram, didn't we? Well, what does that imply? If they're to the right, it's a lower temperature. But if they're at the top, what does that mean? That's a higher luminosity. How can you have a higher luminosity with a lower temperature? What else did we say about upper right? That's a large star. It has a lot of surface area to emit light. Okay, so again, you see how they all work together? And likewise, down in the lower left, our white dwarf stars, we would say are hot but low luminosity. How do you get that? Small size. Okay, so once again, at a glance, you can really understand quite a bit about them. That stellar size increases from lower left to upper right. So we've done a nice job, I think, describing all the various stars on there. There's one more thing we're going to talk about. I've touched on it just briefly, the lifetime. What do I mean by the lifetime? Well, it's just that. How long will that star last? Why would a star not last forever? Why is a star a star? It's making energy. Can it make energy forever? Can't do that, okay? So when we talk about lifetime here in green, what we mean is the lifetime of the star on the main sequence, okay? So let's talk about what happens after that. In other words, eventually the star in its core is going to fuse the hydrogen into helium, and it's going to run out. It's going to use up all the fuel, just like you used up all the gas in your tank, right? Well, if it's not fusing hydrogen to helium in its core, it's not going to be on the main sequence anymore. Turns out when this happens, all stars go through this. They begin to move up and to the right of the main sequence. Now, we can't watch that happen overnight. This takes many, many years. But we can take a snapshot of many stars and see them all at various stages. So in other words, really all stars are going to move up and right and become either giants or in a few cases supergiants, okay? And that's where those stars come from. In other words, giants and supergiants are not just large in size, they are stars that are no longer on the main sequence. They're no longer fusing hydrogen into helium. So we're seeing the first example here of what came to be known as stellar evolution. The stars are changing, okay? We're going to get into the details here for a few minutes, but essentially the lower mass stars down here in the lower right are going to move up and become the giants. Our higher mass stars in the upper left are going to move over and become the supergiants, okay? So it's our first look here, again, at stellar evolution. Going back to this idea of lifetimes, I've already said that that depends greatly on the mass. So let's take a couple of examples. We have been able to determine with the theory of stellar evolution, the sun's main sequence lifetime is about 10 billion years. Isn't that just mind-boggling? We know from other sciences like geology that Earth is about half of that, roughly speaking, a little bit less than 5 billion years old. So it makes sense the sun would be the same age. So the sun is about halfway through its lifetime on the main sequence. But let's do a couple of quick calculations you see here. Let's start with a high mass star with 10 times the mass of our sun. Yes, it has 10 times as much fuel, but it's going to burn it 10,000 times faster. My goodness. Well, if you divide that out, you can see that its lifetime is 1,000 times shorter than the sun's. Can you see that there? 10 million years. Oh, that's just a brief time for a star, right? How about a low mass star? Maybe a star with only 10% of the sun's mass. Yes, it starts out with less fuel, but it burns it much slower. Only about 1% as fast as the sun, and therefore it has an extremely long main sequence lifetime, 100 billion years. My goodness, the universe is only 14 billion years old. So that star is nowhere near having used up its available fuel. So can you see, again, the great disparity, the great difference, great range of lifetimes on the main sequence based on mass. Okay, so let's take just a couple minutes then and look and see what happens after a star leaves that main sequence. I said it's going to move up and to the right. It's becoming larger, cooler, and more luminous. Why? How does it do that if it has used up the fuel in its core? I'll try to keep this brief. The core is not pouring out enough energy as it used to hold the star up, so it begins to shrink. Gravity says, well, I'm going to squeeze you down, okay? But as that happens, the material outside the core, which is quite hot, it's not quite hot enough for fusion. It falls inwardly too and becomes hot enough for fusion. You follow me? So now we get a spherical shell of material around that core that begins fusing and begins giving off more energy. Well, that extra energy is what expands the star bigger. This shell of fusion, the overall luminosity of our star increases, it moves up. The outer layers are expanding farther from the center, so they are going to be a lower temperature than they were. Our star shifts right on the diagram. Okay, we now have what we call a red giant star. So interesting what's happening inside has a great effect on what we see outside. Well, that core, remember, fused hydrogen into helium. What happened to the helium? The helium is in this core that's slowly getting compressed smaller and smaller. It's getting hotter and hotter, and it's going to reach a critical temperature. It's going to begin fusing. So now the star has a second major source of energy. That helium in the core begins fusing. It adds its energy. That's going to add to the energy of the shell. Okay? What's that going to happen? Our star is going to move from the upper right back down towards the left across the diagram because its surface temperature is increasing. Now, our star is still larger than a main sequence star, so it's above the main sequence. But if you can see where that first arrow kind of ends there, that horizontal branch star is going to fuse helium in its core, hydrogen in a shell. Nice. The star gets to live a little longer, right? Well, turns out helium fusion does not last as long as hydrogen fusion, so after a relatively shorter time, the star's in trouble again. That core shrinks again. The first shell falls inwardly, gets hotter, it begins fusing helium. A new shell forms fusing hydrogen. Our star moves up and to the right a second time as a red giant. Again, we're not going to be able to watch this happen overnight, but it does happen. So we got two shells providing energy, but that doesn't last very long at all. The star is starting to become unstable. It's starting to pulsate. Sometimes it produces a little extra energy when it's smaller and it expands the star. Oh, I went too far. I'm going to cool back down and come back down. Our star starts pulsating, and essentially that becomes unstable to the point that the star eventually must change. What happens to it? It's going to expel the outer layers of the star about like that. It's an unstable state for the star. Much, if not most, of the outer layers of the star are expelled out into space. We see these beautiful images over on the right. We call these planetary nebula. It's a really bad name for it, because they have nothing to do with planets. But early astronomers would look in their telescopes, see this little round, oh, it looks like a planet. No, it's not a planet. Okay? Now, this is a relatively brief phase as well. The star expelling this matter, as you can see in our animation, it eventually dissipates. So because it's a relatively brief stage, we just don't see that many of them. Okay? We don't see that many of them because, again, this can only take maybe 100,000 years or so, something like that. So this is the end for our low-mass star. It has gone through these stages that we walked through. Eventually ejects its outer layers. What's left? That small, hot core. It's very dense, very hot, because it's been fusing. This now is our white dwarf star. This now is our white dwarf star. You can see in one or two of the pictures there, you can kind of see an image there of that. Okay? So here then is just a quick summary. I won't take you through the whole thing, but our star moves up and to the right after the main sequence. spends some time as a red giant, expels those outer layers, and ends up in the lower left as a small, hot, dense white dwarf star. So here's our summary. Low-mass stars, again, use their fuel slowly, live long lives, expand into red giants, eject those outer layers, and end up as white dwarfs. But is our high-mass star going to do the same thing? You can probably guess it's going to be a little different. That's why we break them into two main categories. High-mass stars, we said, are going to burn their fuel much faster. So they're going to have shorter main sequence lives. Now, they can't really make much more energy, so they don't really go up very far. But they will move across our diagram, and they become supergiants. Previous to this, they were main sequence stars, but now they're supergiants, okay? The mass of these high-mass stars is such that every time it runs out of fuel in the core is going to contract a little, and another shell is going to form, like we just described. And then the core is going to burn some fuel, and then it's going to shrink again, and then a new shell is going to form. But rather than stop at just 2 shells, our high-mass star will continue on making more shells. The term for this you see here is nucleosynthesis. It essentially is taking hydrogen into helium, into carbon, into oxygen, into many other elements. It's going to make more shells of what we call heavier elements. Okay, so deep within the star, this is created, and as I just described, it is going to happen more quickly than in the low-mass star. Here's a diagram of what I'm describing. You can kind of see the various shells deep within the star. Meanwhile, there's still this huge outer region of hydrogen gas, but here is where heavier elements are made. The greater mass, the stronger gravity heats that core hotter and hotter and hotter each time it finishes fusing into the one element, it contracts, gets even hotter, fuses the next element. Meanwhile, another shell forms, and another shell, and another shell. So we get multiple shells. Again, why? The greater mass, the greater temperature, higher energy fusion, heavier elements. How far can this go? Well, it can go pretty far. It can go up to iron. But when our star here ends up with a core made of iron, it's in serious trouble. Iron fusion does not release enough energy to hold up all these other layers above it. So here's where gravity's relentless power is going to crush that thing even smaller. Even an iron core, can you imagine that something larger than the Earth made of iron, gravity says, I don't care, I'm going to crush that even smaller. And the star cannot respond. It cannot fuse a new element to make more energy. So what's going to happen? Well, with no support, the core completely collapses. It's crushed, essentially, okay? And as it gets smaller and smaller and smaller and denser, it's going to reach a certain critical density. It's quite extraordinary, and that's enough. Everything else is falling inwardly towards this core, and when that core reaches that density, it's going to literally bounce off of the core. Imagine the energy released, as you see here, in what we call a supernova. This is when a high-mass star explodes and tremendously increases its luminosity in a matter of hours. During this phase, during this brief time, and for a few weeks afterwards, as that outer shell is now racing outward, there's tremendous energy here that can actually fuse more elements during this brief time in the shells. Heavier elements that we see on our periodic table of elements can be formed here. And the other important factor here is all this material is spewed out into space. So these supernovae create and then disperse heavy elements out into space. We use the term that they enrich the interstellar medium with these heavy elements. Those material can eventually cool down. Gravity can start to compress them again and form a next generation of stars. Those next generation of stars have an increased amount of heavy elements in them, And when they spin and flatten, their disks of material have those heavy elements in them. And any planets that form in that disk have heavy elements in them, like ours. So when we look at Earth and we dig in the Earth and we dig up all these various elements, those elements were formed by supernovae explosions in the distant past. Kind of interesting how nature can do that, isn't that? Planets like ours are formed from these heavy elements formed during a supernova explosion. There's one example, a famous one, the Crab Nebula, of what it looks like after roughly 1,000 years. This thing is just racing outward, expanding in size, and it's quite a sight. Quite a sight. But we still have yet another question, as we often do, right? What about the core? Remember, it was all crushed and everything bounced off it? Whatever happened to that thing? Well, here we're going to get into our last couple of points about the extreme, and I do mean extreme, density of that little tiny remaining core. In most cases, that core is now going to turn into what we call a neutron star. Why that? Well, in stars that are more massive than the sun, but perhaps up to roughly, maybe 10 solar masses, as this thing is collapsing inwardly, gravity is so powerful, it can take a normal atom. You remember normal atoms have their little nucleus and the electrons, right? And it can crush those electrons inward into those nuclei. That's just unprecedented compression. And when the electrons meet the protons in the nucleus, they turn into neutrons. And normally, atoms have a lot of space between their electrons and our little nucleus. But all that space is now gone because they've been crushed into the nucleus. So in other words, the densities here become, well, astronomical. Forgive the pun, but okay. Neutrons are squeezed together so tightly that only their extreme density of themselves can literally stop this thing from going any further if the star's mass is no more than, you hear different numbers, 8, 10, 12 times the mass of the sun. Okay. And we have a neutron star. Look at this number here briefly. 1.5 times the mass of the sun, but a radius of about 10 kilometers. That's about the size of Glen Ellen. Can you imagine squeezing the sun down to the size of Glen Ellen? What the density would be? Mind-boggling. Back when we talked about white dwarfs, they were compressed down pretty good. We sometimes say, maybe a little cubic centimeter of a white dwarf might weigh a couple of tons. That's pretty dense. But here it can be millions of tons. And something the size of a sugar cube, it's just mind-boggling, isn't it? But what about the most massive stars of all? Those are greater than even 10 solar masses. We'll just use that number. Well, in this case, gravity is just overpowering. Even the neutrons, we don't think, can hold up against it. And they are crushed. So the contraction just continues smaller and smaller and smaller and smaller. How far does that go? Here's where it gets a little hard to understand. Mathematically, they approach a size of 0. So what does that mean, a size of 0? Well, the density then would approach infinity. Kind of mind-boggling. This is what you've come to know as a black hole. Now, does that mean this thing just disappears? No, mass cannot disappear from the universe. So the mass remains, the gravity remains, but why is it called a black hole? Well, because the gravity is so strong that not even light can escape this thing. A neutron star, if you look closely here, the escape velocity is about 70% of the speed of light. But when you reach a certain number, about 3 solar masses, even light cannot escape. So this is how black holes form after a supernova explosion of a very high mass star. Okay? So what do you think about the life cycle of a high mass star? Wow, we could talk a long time about that. Again, they are burning that fuel quickly, live a short life, expand now into supergiants, explode as supernovae. Years ago, we'd watch anxiously for one. These days, we have telescopes watching anxiously for them. And as soon as one is spotted, they immediately notify astronomers all around the world, and pretty much everybody will aim their telescopes. Let's get some more information. Let's get some more light from this thing. Okay. And quickly, we will determine, we have ways to determine, did it turn into a neutron star or did it go all the way to a black hole? It's a pretty amazing field. Okay. So here, in conclusion, is a summary of all we've talked about today. We talked about, of course, stellar formation there to the left. We can end up with a relatively smaller, lower mass star or a larger, higher mass star. Our smaller, lower mass star eventually is going to leave that main sequence. It's going to become a red giant. It's eventually going to expel its outer layers as a planetary nebula. We end up with a white dwarf. Our high mass stars are going to swell into supergiants, and when they can no longer survive, they're going to explode as a supernova, leaving us either a neutron star or a black hole. So I'll let you look at all those various steps there that we talked through, okay? So this is the grand story of stellar evolution that we have pieced together in the last 100 years or so. I think it's an amazing story. It's a mind-boggling story that we humans can look out and piece this all together, number one, but what's really going on in our universe? So I hope you've enjoyed that. Let me finish just with this question. What does this all mean to us? And just a few thoughts here. Maybe you'll have a few. As I just said, this magnificent story really humbles us. Here we are living on this little planet, circling a very nice medium mass main sequence star, and we look out into this universe and see all of this going on. And we can piece together the story, can't we? We're not going to sit around for millions of years, but we can see stars at all these stages and piece it together. We also learn about the billions of years of stellar evolution that are required for this to happen, starting with star formation, main sequence stages, right? Giants, red giants, all that, and finishing with these supernovae. And how important is that? Well, again, one last time, the heavy elements essentially are what our planet is made out of. We happen to be on a small object that is highly enriched in these heavy elements. Most stars are mostly hydrogen gas, a little bit of helium. Many planets are hydrogen gas, but our planet is enriched greatly in heavy elements. In fact, the very atoms, not only in our planet, but in our bodies, were made in high-mass stars. I think that's a mind-boggling thought. Some of you might remember, long ago, there was a famous astronomer, Carl Sagan. You remember that name? Some of you are smiling and laughing. He used to say, "We are made of star stuff." I think that's a very interesting comment when we consider the story of stellar evolution. The final piece, of course, as I said, is, of course, our well-behaved, very friendly sun is just the right mass to provide just the right energy for planets like ours to have life. So here we are, and we can ponder and learn about this amazing universe. So give that some thought. Thank you very much for joining me tonight. It's a pleasure having you. Hope you come back and see me again. Now it's your chance to fire those questions at me. You can have at the astronomer here and see what we maybe can explain better or something you want to go a little farther. Okay, so just go ahead and raise your hand. While we're getting ready for the microphones, let me just always make my little pitch here just to remind you that out on YouTube I've got 2 actual small courses. These are relatively short. A lot of what we talked about tonight is encapsulated in the one on stars and galaxies. But I've also got a nice little course here for you on solar system astronomy, if you're interested in that kind of thing. All you got to do is type my name in. You'll find the courses out there. A lot of people have enjoyed those. I hope you will. And presentations like this one are also out there. Going back a number of years, you can see some of our recent ones on the James Webb Space Telescope. I couldn't resist doing one on our magnificent home, the Earth. How can you not do one of those? Story of the solar system, on and on. So plenty of things to keep you busy when we can't be here together. Okay, let's take those questions. Who wants to get us started? One over here in the front?
Yeah. Where does the Big Bang fit into this story?
Wow, there's a question. I'll have to keep that one brief. The Big Bang, of course, is the beginning of the universe. And we know that there was a beginning because we see the entire universe expanding. We can measure that motion with the Doppler shift and other ways. And so the Big Bang, interestingly, we think was pretty much only hydrogen. But during its very, very, very first few moments, it was hot enough that it was fusing that hydrogen into helium. That stuff spread out as space expands. And as we described at the beginning, now stars can form from hydrogen and helium, and that's where this story picks up. So that's really the beginning of the story, is the Big Bang. Okay? Next question over here. Sure, go ahead.
I'm confused I get confused visually by that HR scale.
Okay.
Because traditionally, red is hot and blue is cold, and it's reversed. So you're telling me, it's like I'm hearing something and my vision's telling me the opposite.
Yeah, excuse me. So you're right, we're used to red being hot, red hot fire or something, right? But it turns out, in physics, the hotter objects get, their light that they're giving off, excuse me, becomes bluer. So I know it seems opposite of what we're used to in our everyday life, because we don't usually experience objects that are blue hot. Think of the gas on your maybe gas range. You've seen a little blue flame there? That's pretty hot. It's actually technically hotter than the orange or yellow flame from a campfire, but the campfire is much bigger, of course. But if you were able to somehow reach in and measure the blue flame and the red flame, the blue flame would be hotter. Okay? Another question over here? Sure, right down in front here, I think we got one. And then we'll get right to you in just a minute, but we already have one. Go ahead, please, with the microphone.
So even though it takes millions or billions of years for the lifespan of a star, if it eventually ends up into an infinitely smaller and smaller, compressing or into a black hole, is that the end of it?
That's a good question. I have a whole lecture on black holes. I really do, actually, on YouTube, so go out and watch that. But the short answer would be, is that the end of it? Yeah, almost. We can pretty much think of black holes as, yes, the end of that object. Now, a black hole can bring more matter in, and it can grow in mass. And we can now find ways to study black holes. Stephen Hawking was the guy who discovered probably a very, not an exception, but he discovered a very interesting little possibility. He said it's possible, and this is a long answer, but that a black hole could actually find a way, if two particles happen to wander near a black hole, one might get pulled in and one might escape, and it might look to you and me like, oh, a particle escaped from the black hole. Well, yeah, but it had to pay the price because its partner particle had to get sucked in. So I don't want to go into a lot of detail there, but to answer your question, yeah, black holes are pretty much the end of the story. Yeah, they can change slightly, they can gain mass, and there's other things. I gave the lecture on gravitational waves that black holes can emit, so hope that answers the question. There's a lot to it. Okay, another question here? Go ahead.
I have two questions.
Oh boy.
So, do you think a planet could survive around a brown dwarf?
That's a good question. I'm thinking that you asked that question because I said the brown dwarf does not give off very much energy, does it?
Yeah.
So I'm thinking if a planet was around a brown dwarf, it'd have to be awfully close, wouldn't it?
Yeah.
And that raises other problems. We're all familiar with the tides. You go to the ocean. You ever go to the ocean and you see, oh, the tide, the water's higher and lower, and oh, that's nice. Well, the problem is if a planet is too close to a star to try to stay warm, the gravity of the brown dwarf is going to cause tides on this planet that are not going to be a good thing. I'll keep this short, but so the short answer would probably be probably not. It's not a good place for a planet to live very long. Would the planet physically survive a while? Sure, but if you meant could there be life on it? No, I don't think so. That's probably not a good place to be. You had another question?
I've heard about hypergiants.
Hypergiants, yeah. So what's a hypergiant? Well, we think we may have found a few, a handful, but it's still not quite positive. These are stars that when they explode, they give off, incredibly, more energy than a supernova. And you go, well, how can it be more than a supernova? It would have to be more massive of a star. So instead of a supergiant, now there might be, we think, hypergiants that, boy, when they explode, it's even more. We think that might have been more common early, very, very early in the universe. The very first stars could have been hypergiants, and when they exploded, it was like that. We hardly ever see that kind of thing today. Okay, interesting question. Got another one over here? Sure, go ahead.
Yeah, if fusion ends at iron, where do the other naturally occurring elements come from?
Yeah, there's a number of other processes. I'm not a chemist, but certain elements, once they are created, you probably know this, they decay. Some take a short time, some take a long time to decay. Think of even like, say, a uranium, it decays. So there's a lot of chemical processes that will change one element to the other without fusion. And that's where most of them are. I didn't have time, obviously, to put that in here tonight, but in my other classes, we see the periodic table of elements. And you can say, oh, these elements formed in a star, but these were from this, and this is from that process, and that's from that process. The chemists can tell us that. I've asked the chemistry professors, what about that? Yep, that forms like such and blah, blah, blah. It takes this long. We actually use that here on Earth. We have measured how long some of those take, and we can use that as a clock to say, well, how old is that rock? Well, it has this much of this element in it, and it decays like that, so it's that old. Okay, so it's other processes. Yeah, good. And one over here? Sure.
I think real early, like one of your first slides, when you were starting with dust and gas, and you said, I think it was 20 times the mass of the sun or 200 times the mass of the sun was required to form a star. Yet we see stars that are quite smaller than our sun in mass. And so what happens to all the rest of that?
Good question. I think I skipped through that pretty quickly, so my apologies there. But essentially, you start with this cloud. That number 200 means if the cloud does not even have 200 times the mass of the sun, the gravity is not strong enough to even make this whole thing work. So that's kind of your very bare minimum number. Usually those clouds are thousands of times the mass of the sun. But then I also skipped through this quickly, I remember. As that thing starts to contract, it starts at a certain kind of critical step, it fragments into pieces, so to speak. And instead of having something with 5,000 solar masses, now you have a bunch of ones that are maybe only 10 or 5 or whatever like that. Those then go through that stage. So thank you for helping me to clarify that a little bit. I think I kind of went through that quite quickly. Okay, another one over here, please.
If the singularity at the beginning of the universe is a black hole of sorts, so that begs the question, were there events prior that formed it, just like the events prior to forming a black hole?
I knew I shouldn't have taken this question. I knew it. Good question, actually. Just kidding. So we can view the beginning of the universe, as you said, as this incredibly tiny, incredibly dense thing, and you say, well, that just sounds a little bit like a black hole, because the center of a black hole is called a singularity, he mentioned. So where'd that come from? That's a big question. And the short answer I would respond to that with has to do with, well, so a black hole today, we can't know a lot about it. Its gross properties, sure. But if you ever said, well, what's inside of it? We can make some educated guesses, we can do some calculations, but we can't look inside of it. Why not? Because no light comes out. So I'm not fully versed in the very latest on the very beginning of the universe, but the short answer is still, it's really hard to push beyond the singularity that began the Big Bang. In a sense, I think maybe you're asking, so what caused that Big Bang to bang, right? What caused this tiny, infinitesimally tiny point to explode? That's a tough question. There's some ideas, but I don't think we're there yet. Okay, I hope that's a good enough answer. Another question?
On the HR diagram with respect to color, How come there's no green?
Oh, that's a good question. Whoops, going a little too far there. The short answer there is color is something that you and I experience or interpret, however you want to say it. Okay? And technically speaking, yeah, green would be somewhere in here, right, between blue and yellow. But that's where you and I experience white. All the colors tend to mix together to our eyes. So when we use the word color, no, there's no green stars because you and I experience that as white. It's more of a factor of our experiencing color as a function. Okay, good question though. I've seen that before somewhere. Okay, one over here somewhere? Way over here?
Yeah. The sun is the second or third generation star in our region of space?
Yeah, that's a good question. So I described how you have these high mass stars form. They don't live very long. They explode. They seed the interstellar medium, and then the next generation of stars forms from that. Yeah, we think the sun is at least a second, if not possibly a third generation star. It has a moderate enrichment of heavy elements. When it formed, what do you think was in its disk? Heavy elements. What do you think we're standing on, right? So yes, the sun is clearly not one of the original stars in the universe because those didn't really have any heavy elements. So good question, yeah. We've been through several generations. Hard to be exact. Over here?
Hello, Professor.
Hello.
Just a question. You said that in the black holes, and you've said in class that basically what happens is that matter just collapses in a basically infinite point. But, well, Stephen Hawking was recognized because he said that even black holes have an end when they evaporate.
Yeah.
And for that to happen, it's just logical to assume that a force kind of needs to overpower that gravity for the black hole to evaporate or end. Okay. So how does that happen?
Let me go back to, I started to answer this. I kept it brief. I'll try to. So there's these well-known and documented and essentially proven phenomena that at first you might say, come on, that can't happen. Scientists have found something called virtual particles, if you want to look that up. So virtual particles kind of take advantage of a loophole, right? We all know that stuff doesn't just magically appear out of space, right? Or does it? Well, long ago, scientists said, you know, what if a particle could kind of get away with it for a very, very tiny amount of time, just pop into existence, if its antiparticle would pop into existence with it, and then they quickly destroyed each other and just went away and nobody noticed. Sounded kind of crazy at first, like, really? Yeah? Well, guess what? It really happens. We've seen it. We've measured it. Virtual particles. Look that up. So Hawking one day was thinking about that. He's like, well, wait a minute. What if this pair of virtual particles suddenly appeared right near the edge of a black hole? It's called the event horizon. And one of those particles fell in, but one of them somehow managed to escape. What would that look like? Well, it would look like the black hole allowed a particle to escape or emit the particle. Now, you got to understand that when these particles appear, one is considered to have a positive mass and one has a negative mass. Well, if the black hole takes the one that's negative mass and this one escapes, the black hole is essentially gaining negative mass or losing mass. This is the idea of evaporating black holes. So when he did the math, it came back like, well, that's going to take a really long time. Particle by particle by particle, yeah. So that's kind of what you probably heard. And we think it does happen, but the time frames involved are exceedingly long. So as far as a black hole evaporating, I forget the exact numbers. It depends on the mass of the black hole. If you start out with a nice small one, it's not going to take as long, but a huge massive one's going to take long. They are just exceedingly long periods of time. I don't want to guess. I want to say it's billions of years or something. Okay, so you gotta. That's what you heard there, Dave.
It's not really an astronomy question, but maybe others were wondering also. It confused me why, for your bar graphs, especially right there, surface temperature, why are the cooler stars in red and the hotter stars are in blue? I mean, usually we think of it the other way.
Yeah, I think we had a similar question earlier where I was explaining how even though you and I are used to saying, oh, that thing's red hot, blue's hotter. And I think I used the example of the blue flame on your gas stove. If you somehow could measure that safely and you measured the red from a fire, the blue would be hotter. It's just bluer because that's shorter wavelength light coming from a hotter object. It's a little bit like that whole thing I talked about with, if you look closely here again, our star that is shown in blue curve, they chose blue because that's a hotter star. Okay, so it's just a matter of how you and I interpret color, and it's a matter of kind of our everyday usage. We're used to saying, oh, it's red hot. Well, frankly, blue is hotter. It just is. Okay, any other ones? One more here? Yeah, sure, go ahead.
Yeah, I know that mass and weight are not equal, but we have units for weight, kilo, pound. Is there a unit for mass?
Yeah, generally the unit we use for mass is kilograms.
Oh, it is?
Yeah, because it can be defined that way. And then yeah, you're correct when we talk about weight. Weight is more a measure of the strength of gravity you're in. If I weighed, well, I won't tell you, so many pounds, and you probably know this, some of you remember as far back as when our astronauts were on the moon, they were bouncing around, jumping up in the air. Why? They weighed less because the moon's gravity was weaker. Did their mass change? No. So yeah, weight and mass are different things. The unit for mass is kilogram.
Okay. Could you go up maybe 1 or 2 slides where you have some of the math problems?
You like those, huh?
No.
No.
Okay,
No, I
okay,
didn't.
okay.
Oh, right there?
All right. It goes back to units.
Okay.
Our father was a chemist, and we had
Oh,
this
boy.
drilled into us. Okay. So now we're talking about on the left side, you've got, say, kilos.
Okay.
Okay. A is separation, that's distance.
Meters.
Meters, whatever, light years.
P is in seconds.
Okay.
Uh-huh.
How do they come together?
How do you get to the units?
Yeah.
Come to class.
Huh?
Come to class, I'll show you. Stay after, I'll show you. I'll pull up another lecture if you want to see it, I'll show it to you. But to try to verbally describe it, it might be more confusing than to literally show you something. But yeah. Anyone else? Another one here? Sure, we got good questions tonight, very good.
So this may be a silly question. You said the core gets to iron, and then supernova creates heavier elements. So I immediately looked up what's heavier than iron, and there was gold, silver, and copper. Is there a gold planet out there somewhere?
No, but there's gold in your jewelry, isn't there? Yeah. And that was maybe not the most precise usage of the language there. I didn't only mean elements heavier than iron, although that is true. That's where it's made. Yeah, gold is made there. So everybody's got a little bit of gold jewelry. You got just a tiny little piece of a supernova, you know, on your finger. Or on. So it is kind of mind-boggling. And many of the elements that are created during the supernova, back to who was the chemistry? They don't live long. They decay into others. And it's interesting, we can actually use that when we see a supernova go off. Astronomers know, okay, so here's what's pretty much going to happen. We've got a pretty good idea. These elements are going to form quickly, but these elements are going to decay into the next like radioactively. And some of them only have half-lives of a few days, a few weeks, a few months. There's even one particular situation where they almost expect, they go, so the supernova is going to do this now because the radioactive, I forget what it is, aluminum is going to change into nickel or something. I gotta ask my chemistry friends. This element's going to decay into that, and we're going to see a little extra, and there's a little bump in luminosity. You go, there it is, it just changed. So it's kind of neat for them to give us the details. I don't have all the details memorized, but yeah, all these elements that are formed. Some live much longer. You know, some live much longer, of course, and some don't. And that's how our periodic table gets all populated. One more here? Yeah, go ahead.
I saw that our sun's like its maximum luminosity on either one on that was on the side. It came down right in the middle of the visible spectrum.
So are you talking about the HR diagram?
Yeah.
No. Okay, so let's get one of those here. Okay, and
Wait,
you noticed
no.
our sun is right smack in the middle there, right? You can just barely see it. But go ahead.
It's Wien's
The,
law.
Wien's law.
Okay. Oh, and the Wien's law graph. Let me back up to that. Okay, so we just happened to choose, we figured we were all interested to see our sun represented, you know, on that graph, so we wanted to put the sun in there. Is that what you mean right there?
Yeah.
Okay.
It goes plop down in the middle of the visible light.
It does.
Is that why we can see like all red, yellow, blue, green, purple?
That is exactly why. I'm so glad you brought him. So think about it this way. There's two ways to look at that. So the sun has a certain temperature, and it gives off this spectrum, and its peak wavelength is invisible light. And wow, life on Earth lives primarily off visible light. A little bit of infrared, a little bit of, okay, those are more minor, but we live off, is that a coincidence? No, of course not. Life needs to work off of visible light because our star gives off mostly visible light. If life depended on more, you know, infrared light, wherever on the right, well, our sun doesn't give off so much infrared light. So do you see the point? Wow, the sun is essentially determined how life needs to absorb energy. It's going to be visible light. Okay, well, we'll absorb the visible light then. And good point. You caught that. That's very good. Yeah. Some have speculated, well, what if we found a planet orbiting a different star and it had a different peak wavelength? Would it absorb light differently? Maybe. Wouldn't that be interesting? Found some kind of plants that absorb more ultraviolet light or something? Be like, that's kind of interesting, right? So very good point. Yeah, you caught that. Nice. Any more? You guys have good questions. All right. Well, again, I want to thank you. And if anybody does have more, I'll be happy to stick around a few minutes. But thanks for being with us tonight. Have a great night.